All right, so last time what we did was we showed the Cauchy-Riemann equations. Okay, since they're so critical, let me recall them. Right, so we saw that if f, right, we could write like f of z is analytic, say f of z. Right, then we could write f x plus iy, right, where x and y's are real, as u x and y plus I v x and y, right? Where these are both real. So functions now viewed from R2 to R. Well, someone asked if it's recorded. Yeah, I record over YouTube and also on a local setup. So it's being doubly recorded for redundancy. Hopefully, at least one of them will work. So yeah, thanks for pointing out. Yeah, the recording on Zoom you can't read so well anyway, so I just stopped doing it. Yeah. Okay, so then if we have this, then what we saw was U and V satisfy the Cauchy-Riemann equations. Okay, so in particular, they satisfy this. All right. And this was sort of the first example in which we saw that differentiable complex functions are very special. Right? This notion of analytic is very, very special. In particular, the real part and the imaginary part need to be very intertwined, very related. Right? And then we even use this to show that actually, as long as you can differentiate twice, as long as you can differentiate them twice, then actually the functions are harmonic, right? U is harmonic. We did the calculations and we showed that was the case. And in fact, given U that satisfies this, for which there exists a V that satisfies these equations, then we actually call V the harmonic conjugate of U. Right? And this shows up also in the theory of differential equations. We saw all this last time. And I even gave you a little challenge of I give you a function U that was harmonic and I ask you to find the harmonic conjugate and to show what is the function that corresponds to it, right? And so I just saw here on the corner of my eye in the chat, someone asked if here this is an implication or an equivalence. Right, so for now, all I'm saying is that this is an implication. What we're going to actually do now is going to show that this is in some sense an equivalence. Right, and it'll actually be an equivalence in a very strong sense. And so someone pointed out to me like last week or something, a very good point, which is so far, we haven't very much taken the theorem proof type approach, right, and neither does the book actually. Right, the book for now at least doesn't do very much theorem proof. This is definitely going to change at some point. I would maybe say that this, for now, where we are, sort of the results that we obtain, they come naturally by thinking about, right? You sort of explore, right? You had this new notion of differentiability over the complex numbers, and it makes a lot of sense to try to imagine what happens if the limit is taken from perpendicular directions. Right, and so we took the limit from the reals, from the purely imaginary numbers, and the Cauchy-Riemann equation sort of jumped out of that. Right, it's not that it made sense that this would be true because we somehow suspected this to be true, and then we went and tried to prove it. Right, it was just exploring what this type of differentiability gives us that we derived these equations. Right, sort of the finding of the theorem is the proof itself. Right, and so. There are results in math that are more of that style. There are others in which sort of the theorem is something that you might suspect, and then you have to prove it, right? The converse of this, however, is of the second type, right? Because it's a very natural question now, right? As a mathematician, well, okay, this is an implication, but is this actually equivalent, right? Do we have a converse, right? Is there a converse? Right. This is a very natural mathematics question, right? And it's not like, we sort of, the question suggests the possibility of a certain theorem, right? That if U and V satisfy these equations, then they form F that is analytic, right? And so in this case, right, the theorem proof approach makes a lot more sense. And indeed, we're going to show now that this is the case. You can now, go and battle sort of how little assumptions on smoothness you can put on U and V. We're not going to do this for now. I'm just going to assume, what I need and not worry about whether they're the weakest possible assumptions. And then later we will revisit this. Okay, so this gives us the theorem. If, let's say, U, X, Y, and V, X, Y, right? So functions from R2 to R, or at least from an open subset of R2 to R. RC1, right? So their derivative is they're differentiable and their derivative is continuous, and so they have continuous derivatives. Okay, so maybe call this this I'm going to call the Cauchy-Riemann equations. And satisfy the Cauchy-Riemann equations. Then f of z defined as is analytic. Okay, so we'll prove this theorem. It's actually, it's not so hard. I mean, it goes very much how a lot of the theorems in real analysis also go. Right, so because, so proof of this. Right, okay, before proving this, maybe I should say another word of just a bit more intuition, right? Because, in a way, the proofs, you can easily read them on the book, but the intuition is not always there, right? So, as we'll see later, it's not yet clear, but as we'll see later, functions that are analytic, actually, we're going to be able to differentiate them many times, not just once, right? And so we have this phenomena here that if we graph, right, if the real part and the imaginary parts are differentiable just once and continuous, and the derivatives are continuous, and they satisfy these equations, then they're going to form an analytic function which will force basically everything to be differentiable as many times as you want, right? So it's one of these instances in which having functions that maybe are only required to have one or two derivatives, but which satisfy a certain differential equation will force them to actually be much, much smoother, right? And there's many examples of this in differential equations, right, in which solutions to things like diffusion and so on are always extremely smooth, right? And so there's a whole sort of industry in the theory of differential equations of trying to show that if something is a solution to some differential equation, even if it involves only, say, derivatives of order 1 or 2, actually the functions immediately need to be super smooth, like maybe differentiable even an infinite number of times. Right, and so you'll get the exact same phenomena here, and you could go back to the theory of differential equations and see that basically that's what's going on, right? That's one way of viewing what's going on here. Okay, so the proof of this, there's a fair amount of calculations, so let's just go through it. So the idea, right, the idea is simple, okay? Maybe before doing the calculations, let me explain what the idea is. The idea is just write U equal to its first order approximation, right? The U, U of x plus t and y plus, say, w will be equal to uxy plus sort of its first order approximation as given by the first derivative, right? And continuity of the derivative will mean that the error of that is quite small. You do the same thing for v, right? So you're using the fact that the derivatives exist and are continuous, and then you write out f in that way, and you just try to prove that the limit of the derivative exists, right? That's exactly what we're going to do, right? We write sort of differentials in f and v in terms of the derivatives, and then we expand f in terms of u and v, and we try to prove that the differential in the sense of the limit that shows up in complex analysis, it's a proper limit, and then the derivatives are given by what you would expect them to be given. Okay, so let's do it. Try to use the as consistent as possible with the notation. Okay, because u as there's derivatives, we have that this, right? This difference is basically t times the derivative of u with respect to x, right? And of course, it's at the point xy, but I won't keep writing that, otherwise it's just too much. U y plus some error, right? And this, and the point is that this error over, right? This error goes to 0 faster than t and w, right? In particular, if I write this, right, as t and w go to 0, this goes to 0 too, right? As t and w go to 0, right, this error goes to 0, right? Okay, so we do the exact same thing for v. Plus epsilon 2 error is the same thing, right? Epsilon 2 goes to 0 as t and w goes to 0. Okay? Okay, so now let's see what we get. Maybe I'll put this here. Okay, so now we write for z. Say, okay, so let me identify, right? I've been doing this a lot. Let me make more explicit. Identify z with x plus I, y, right? And now f of z plus t plus I w, right? Now minus f of z, right? What is this equal to? This is equal to, okay, so u x plus t y plus w minus u y plus I times, now the thing in b, dx plus t minus b. Okay, now we need to expand all this out. Okay, so I just expand using all of this. Let's see if I can do this without making a mistake. Okay, plus the error term. Let me deal with that later. W, V, Y. Plus epsilon 1 plus epsilon 2. Now, okay, so now let's make all the derivatives with respect to x, right? Because we know that, the derivative that, right, like if I want to make understand what this is, write out the derivative of f, it doesn't matter which direction I do it. So it'll be easier for me to argue this if I write everything in terms of the same variable, right? Because it should be the case that, if I do this, it should be the case that this should be the derivative of f in the complex analysis sense times the differential, right? And so the derivative of f should be the same if I do it in any direction. So I'm going to try to write everything in the direction of x. Okay, so basically what I'm going to do is I'm going to use Cauchy-Riemann to switch these, right? The ones in terms of y. Okay, I could just do it, but this is not coming out of the blue, right? You want to make, yeah, okay, maybe it'll be clear after what I said, and now that I just do it. Okay, so u with respect to y is minus, hopefully, no. Okay, so u with respect to y is the same thing as minus v with respect to x. Right, plus yt. Now it's the same thing as u, and this I leave. And now this one is the same thing as u with respect to x. Okay, plus epsilon 2. Okay. Okay, so now we have to factor this. Right, so in particular, I would like something, okay, I'll just write it, but it's one of those things that now it's easier to just see it happening, and then we can talk about it. Right, because I want the derivative of f to look like this, right? It needs to be the derivative of the real part plus I, the derivative of the imaginary part. Right, but now what terms do I have? I have a t here. Right, this term is now the product of these two, and this one becomes a product of these two plus IW, and so plus IW times the partial of u with respect to x is this term, and this partial plus IW is just minus w times this partial plus, of course, the error. Right, so basically I have what I need. Right, because now the difference between the differential on the function is given by what I would think is the derivative times the size of the differential in any input. Okay, so let me just do this last step. Again, remember, right? These go to 0 faster than t plus IW goes to 0, right? So if I now write f of z plus t plus IW minus f of z over t plus IW, right? The limit of t plus IW going to 0, right? Then this is just. Right, I'm dividing with t plus IW, so I can take this out. This is just derivative of u with respect to x plus I derivative of v with respect to x plus something, right, plus z1 plus z2 over t plus IW, but this term goes to 0, right, by the hypothesis of the continuous differentiability of u and v, and so we're done. Right? Okay, so we know that this is actually equivalent. Okay, so let me see. Yes, someone pointed out. Yeah, right. There is a typo here. Of course, there should be an I here. All over, actually, right here. An I in front of the epsilon 2. Yeah. I mean, it makes no difference, of course. Okay, that's what's correct. Yes, thank you. Okay, so someone asked why, are we done? So we proved that this limit exists, right? So we proved that, the function is now differentiable at z because this limit exists, right? Why? Because regardless of the direction that we take on t plus iw, this term goes to 0, right? That was what made everything work. Okay, so now let's try to actually find some analytic functions. Right? I just convinced you that I've been convincing you maybe for a week or a week and a half that analytic functions are very special and they have to satisfy all these properties and so on. Right, so I've been just trying to convince you that sort of this is a very restrictive definition in a way, right? Because these functions are very special. So maybe at this point the natural question is: are there any? Like, are there any functions? I mean, this is a bit of a provocatory question, right? But it's definitely a fair, right? Do we actually have any? Or are we just, working on complete vacuum where we make all these definitions, but then actually there's no object to study? Right, so what we did see was that, I didn't prove it, but the proof is the same as in the real case, and you can easily do it, that if a function is analytic, then things like the sum and multiplying by a constant or multiplying two functions are analytic, and all this, that these functions are also analytic, and even quotients as long as you don't divide by 0. And so this is one natural way to try to build analytic functions, right? So f of z equals 1 is definitely analytic, right? Because if I think in terms of this limit, I just said 1 minus 1 over, some thing going to 0, but the top is 0 already. So for sure this has a derivative, right? This is analytic for sure. Right, and the derivative of it is just 0. There's another function that's very easily analytic, which is just the identity, right? F z equals z, right? Because, okay, let's just work that out, right? If I do limit of h going to 0 of f of z plus h minus f of z over h, right? What do I get? I get just a limit of h going to 0 of z plus h minus z over h, but this is just 1. So this is equal to 1. Okay, so that's also an analytic function, and the derivative is just 1. Right. So this means that if I now grab the constant function and the function fz equals z, I can now add them, multiply them, and all this. I can create now any polynomial, right? So a very general class of analytic functions are polynomials. Right, so polynomials given by, let me see what are the notation the book uses for coefficients, yeah. Okay, so this is analytic. One important thing perhaps is when we write a polynomial like this, because we want to be able to talk about the degree of the polynomial and so on, we just assume that an is always non-zero. If it was 0, we would just make n be n minus 1 and have that be the last term. Right, so the last term we write, or the biggest degree term, is always non-zero, because otherwise it would actually be natural just to stop here. Right? Okay, so this is analytic, and the derivative we know how to differentiate. I mean, now that we know it's analytic, we can just differentiate normally like we do with the reals. So So I won't do the calculation, but I'll just write down the derivative that you know from real analysis. Okay, so polynomials. Okay, and we basically proved this. I mean, we need the fact that, right, that you can multiply analytic function and still get an analytic function, but which I gave sort of as a homework to check, but it's exactly the same proof as over the reals. And so then, given that, we definitely have this. So, okay, so let me write again. Okay, and its derivative, right, is given by just how we normally differentiate. Right, so if a polynomial has degree n, then its derivative will be a polynomial of degree n minus 1. Okay, so let's see. Let me take a look at the chat. Okay, thanks for the back and forth and for answering some of the questions. So I'll just give a comment for those of you that didn't follow the chat. So right, in real analysis, analytic usually corresponds to, right, you can define differentiable. You can define differentiable as many times as you want, like C infinity, or you can define analytic, and that usually has to do with it to map with it being equal to, say, the Taylor series or something like this, right? So it's something stronger than being differentiable. So in complex analysis, we call the function analytic if it's differentiable. Now, right, this should give you some foresight that, it's definitely foreshadowing the fact that if a function is differentiable in the complex plane, it will actually be analytic in also the sense of the reals, right? And this will be one of the major results. That if you can differentiate once, you can differentiate as many times as we want, and in fact, there'll be extremely nice properties of the Taylor series and so on and so forth. Okay, one thing. And so the function being analytic at a point just means that that limit converges. Then there's something that for now hasn't been made super clear, which is the fact that, right, you oftentimes say that the function is analytic or differentiable or something in an open set or all of the complex numbers or just a set, or you talk about just a point and you care only about what happens in the neighborhood of a point. For now, almost everything that we did is very local, so we just care about a neighborhood at a point. So I didn't worry too much about where the function is differentiable. All you need is for the limit to exist in a point and something to happen around the neighborhood. And so I wasn't too careful about where the function is defined. As we move on and we start doing more global analysis, that starts being much more important. But for now, you can just think of, we're doing very local things. So you only care about what happens near a point. But yes, I agree that, right, it's the name is definitely doing a certain amount of foreshadowing that it's traditionally done. It's not clear that it's the best way, but right, it definitely begs the question of why is it the same name as this very strong definition of smoothness over the real. In the reals, it's because it ends up being the same thing, but you don't know that yet for sure. Right? We don't have yet the tools to say that. Okay, so there'll be a theorem which we'll prove later. So this is known as the fundamental theorem of algebra. Right? We will prove later. Right, that is basically every polynomial right? I mean, we need n bigger or equal than 1. We need at least equal to 1 has a root. Okay, this is what makes a complex number so nice from the viewpoint of algebra, right? If you want to talk about solutions of polynomial equations, right? And then this makes, I mean, it almost makes polynomial equations and solutions over polynomial equations look a bit like linear algebra, right? That we understand very well if we have linear equations, when is it that they have solutions, when it's not. There's all these theorems from linear algebra, right? Because a linear system, basically if it has equations or not, if it has solutions or not, will just depend on some kind of dependencies between these equations and so on and so forth. This will allow you to basically want to develop a similar kind of theory for polynomial equations. I mean, I'm exaggerating it a little, but not a lot. And this is it's at the heart of things like algebraic geometry, where you study solutions of polynomial equations. The same way that you could argue parts of linear algebra, study solutions of linear equations. And if it was doing, say, algebraic geometry over the reals is complicated, because this is definitely not true over the reals, right? I mean, we have the x squared plus 1 example, which was what we used as motivation to create to imagine or create the complex numbers to start with. Okay, and so we won't prove this yet. Turns out that the proof for this actually is analytic. So we're going to use, that might not, that's maybe a point that's worth, thinking about a little, even from a philosophical viewpoint. That actually the proof of this theorem will be using analysis. We'll be using the notion of complex derivative, how being analytic is such a strong property will be at heart of proving this theorem. I don't know if actually there is any proof that doesn't use analysis of this, but definitely the most natural proof that what we're going to do is based in analysis. And it's in a way an algebraic statement. Okay. So I mean, and now, if a polynomial has a solution, we can take, right, there is some alpha 1 that is 0, then we can, basically we know we can divide by z minus alpha 1. Right? I'm sure you've seen this in some algebra class. If not, you can literally just work it out. And, right, so if this is the case, then you can write P of z equals, say, some polynomial, let's call it P1 of z, times z minus alpha 1. And now this polynomial is of degree 1, the degree before minus 1, so it's now degree n minus 1. It will also have a root. You can do this division again and again and again until you have degree 0, and so basically you get n roots. Right, where some roots might show up twice. Right? Okay. If you've never seen that if something has a 0, you can do this, I suggest you just try to work it out. Right? It's obvious that, if alpha 1 is not 0, you definitely cannot do this, because this side is 0, that side wouldn't be. The fact that if it is 0, you can do it is not, completely obvious if you've never seen it, but just, try to work it out. Okay, so this means, in particular, we can write a polynomial P of z. We can write it as a product of just terms like this, right? We call this factoring the polynomial. All right, so there's the number that's not going to go away in this form, and then Okay, where alpha 1, alpha n are the zeros of ETHZ repeated repeated if a 0 is order bigger than 1. Okay, I mean, we don't have to worry so much about this for now. Right, but of course, the polynomial x squared equals 0. X is a 0, but it's a 0 of order 2. Okay, one way to inspect the order of a 0 is if it's is you can see if the derivative is again 0. Right, I mean, that's kind of clear. If you write it this way, then it becomes kind of clear that if a 0 having order 2 corresponds to the polynomial being 0 there, and its derivative also being 0 there. Okay, so let's see if we can get some cool statements out of polynomials. Okay, so let me try to. So there's a theorem called Lucas theorem that I'll prove now. But I want to try to give some intuition of what this theorem is saying. So what this theorem will say, basically, or a slightly stronger version of it, is that if I have a polynomial in the complex plane, and if I put this, call it, let's say that I have a polynomial in the complex plane, right? And I take the zeros, anyway, they're wherever they are. Let's say that there's 4 zeros here. Let me say. Okay, let's say this way. Right, let's say that the polynomial has 4 zeros. Okay, what this theorem will say is that the derivative, if we look at the zeros of the derivative, then the zeros of the derivative will actually need to be inside the convex hull of the zeros, right? Which is a pretty cool, pretty neat theorem that would not be intuitive to start with at all. Right, what we're going to prove is if we have a half space, so if we draw a line, and all the zeros of the polynomial are in one side of the line, then so need to be the zeros of the derivative. Right? And then if you have this, it's easy to see that they need to be in sort of the polygon done by the zeros, right? Because you just have to do this argument for this line, and then for this line, and then for this line, and then for this line, and you see that they need to all be inside the polygon. Okay, now why should this be the case? Let's try to think. I mean, the proof, I'm not sure is that intuitive. Well, I'll prove it to you. But at least let's try to intuitively understand why this should be the case, thinking just in terms of our intuition over the reals. Right? Over the reals, this is definitely not true. Right? Here, okay, I have to convince you that this is a polynomial. But let's say I draw something like this. Right, okay, I have to convince you that there's a polynomial that looks like this, but let's not worry too much about that. It's believable that there's some polynomial that might do this. Right, and if you have something like this would not be the case, right? Because the zeros of the polynomial are this one and this one, right? And the derivative has a 0 indeed in between them, right? And this is easy to see that between two zeros in the reals, there needs to be a 0 in the, right? There needs to be a 0 in between them and the derivative, but there's also a couple more zeros of the derivative here that are not between zeros. Okay. But if a polynomial has all its, if a polynomial of degree n is n zeros, then it's not so hard for you to convince yourself that this can't happen. Right? In the right picture, like the polynomial can't, go and wobble without intersecting the, right? Because the derivative can only have n minus 1 zeros, right? And the function itself needs to have n zeros. And so when a polynomial has all the zeros being real, right? When a polynomial of degree n is n zeros, then what can happen is instead something like this. Okay, this is not a very graceful picture of a polynomial, right? In which the polynomial, say, will have, let's say n is 3, will have 3 zeros, and the derivative will have 2 zeros, right? And the zeros will have to for sure be between the other zeros, right? Because I mean, it goes down and then it needs to go up. Some point the derivative is still zero, right? This mean value theorem. And so in particular, if all the zeros are on this half space, then the derivatives also need the zeros of the derivative also, and the same thing here, right? But proving such a theorem over the reals, you would need, right? You would need to argue that a polynomial of degree n has n zeros, which over the reals we don't, right? This is not true in general. But over the complex numbers will be true, and so we can prove things like this much, much more easily. Okay, just to give you an example of the kind of things that, like, even just studying polynomials would be quite difficult to do over the reals, and over the complex numbers starts being extremely easy. Okay, so let me so I have 3 minutes, let me set up this, and then maybe we'll just finish after. Or maybe I'll just write the theorem statement. I'll just write the theorem statement, and then we'll prove it after the break. Okay, so this is called Lucas' theorem. I'm not sure we're actually ever going to use it, but it's a nice illustration of the power of being able to being sure that polynomials have zeros. And it feels like very geometric, even though the key thing that's being used is in a way of an algebraic. The full zeros of a polynomial. In a half space H, then so are the zeros of P prime of C. Okay, where a half space is just you draw a line and it's one side of the line. Right? Exactly how we would expect it. Right, we tend to write half spaces. The most natural way, write one very natural half space. Maybe let me draw a picture before we go on the break. The very natural half space, of course, is, I have the complex plane is to say this half space, right, the top half space. So the imaginary part of Z being bigger than 0, say. Right, and so that's clear by like translation and rotations. You can write any half space this way. Right, where we know how to rotate, because we know that when multiplied by a complex number, the angles add up. So we know that by multiplying with a complex number, we actually are able to rotate effectively. And so we can define half spaces. I mean, this is something that you'll describe carefully in the book, and you should maybe try to work it out too. But that you can write a half space in this way. I'd say I'm trying to use the exact same notation. Right, so where basically the A gives you some translation and the B gives you some rotation. Okay, so actually they do it with smaller equal than 0, but this would just correspond to this. Right, so how would you write the half space of real part bigger than 0? You just have to divide by I, right? And then you get, you can definitely write it that way. Okay, so let's take a break. And then and then we'll prove this, and then we'll go on. Right? I can give you some hint of what's to come. Right? Polynomials are, of course, a very interesting set of family of functions, but we want to go beyond that. And now, since polynomials seem to be the only analytic functions we can create so far, what we're just going to do is create sort of infinite polynomials, right? And that's why power series and all this start being so. Start being so crucial. And we're going to spend some time just doing a bit of housekeeping around the power series. I guess some theorems are going to be used many, many times. We need to sort of develop a little the language of power series. I'll try to go through it relatively fast.